This is lesson 10 of the chemical bonding storyline. We're moving right along, only 2 more lessons to go. Exciting. As always, the chemical bonding storyline is titled, Why Do Some Things Get Colder or Hotter When They React? We are well into the second part, that is part 2 of the bonding storyline. I've already chronicled before lesson 8 and lesson 9, and that's why I'm referring you to those videos in the playlist. Lesson 10 is really a continuation of the simulation activity that is part of lesson 9. And just like with part 1, the second part of this storyline, all the lessons are nicely connected to each other. The central question for lesson 10, although very related to many of the previous questions, is as follows. Why do some chemical reactions get cold and others get hot? And you're seeing here a screenshot of the simulation, which I will get into in a little bit. First, how much time does lesson 10 take? Not nearly as much as lesson 9. This lesson only took me 1 class period, and my class periods are about 50 minutes per lesson. When did I teach this? I taught this during the 3rd quarter of the academic school year. I'm going to back up just a little bit to recap the very end of lesson 9. What if we could manipulate the breaking and the making of bonds using a simulation? With respect to that simulation, 3 investigations were already completed as part of lesson 9. I will very briefly summarize them here. Investigation 1, how does adding bonds affect the motion of the particles? The stronger the magnetic force associated with magnet 1, the greater the speed by which metallic marble B oscillates, trying to form a bond. Investigation 2, still part of lesson 9, how does forming a bond affect the speed of particles entering and exiting the systems? As the magnetic force associated with magnet 2 increases, the greater the speed by which particle C, colored here in orange, is leaving as a result of its collision with the magnetic marble B. The third and last investigation that I'm summarizing still of lesson 9 deals with the following question. How does breaking bonds affect the speed of particles entering and exiting the system? As particle A is entering the system, this is a non-metallic particle, if it enters the system with enough kinetic energy, with enough speed, it will be able to break the bond that held particle B, a metallic particle, to the first magnet. And as a result of breaking that bond, metallic particle B actually leaves this system, thanks to a complete transfer of speed from particle A to particle B. Lesson 10 is a continuation of the simulation, and the students are asked to set up 3 conditions. First, they have to make predictions. Let's take a quick look at the 3 screenshots that I've created. Condition 1, we've got 2 magnets. Magnetic force associated with the first magnet, labeled 1, and the magnetic force associated with magnet 2. The first condition, magnet 1 and 2 have the same magnetic power, magnetic force. The second condition, the force associated with magnet 2 is stronger than the force associated with the first magnet. The third condition, it's the opposite of condition 2. The first magnet has a greater force than the second magnet. So let's travel to the NetLogo simulation online and actually put in the associated variables. We have reached the NetLogo website. First, we're going to click on Setup. That shows us exactly where we're at right now. And I want to position particle B directly on top of the magnet number 1. So I'm going to move the initial position of particle B to -40 millimeters. If I click Setup, it will move exactly there. I want to move magnet 2 a little bit further over. So I'm going to maybe put it right here at 35, just so that there's a little bit more distance. And I'm going to position magnet 2 exactly at that same spot. And then we're going to hit Setup to reflect that. Now, in order to make these 2 magnets the same strength, I'm going to decrease the strength of magnet 2 to 4, and I'm going to increase the strength of magnet 1 to 4. I'm clicking Setup again, and now they should reflect the exact same strength. I'm going to make the initial speed of particle A 2 and watch what happens. Setup and go. Particle A is coming in, is able to kick particle B, and all the energy is transferred to particle C. But you notice that there's a slight lower speed of particle C compared to particle A. I'm now going to change this first condition where magnet 1 and 2 had equal strength to a new condition where magnet 2 has a much stronger magnetic force compared to magnet 1. I'm reducing magnet 1 to a force of 2. I'm clicking Setup to reflect that. So you now can clearly see that the second magnet has much bigger arrows pointing towards it compared to the first magnet. So that means, in essence, the product bonds are stronger than the reactant bonds. I still have the same speed for the initial speed of particle A. I'm going to click Setup just in case and go and watch what happens. We're breaking the bond between B and the first magnet, and now we're reforming a new bond between B and the second magnet. And we're noticing that particle C, because of that stronger bond, is leaving the system at a much greater speed than the incoming speed of particle A. We're now going to set it up where we're flipping this situation. So instead of magnet 2 having a strength of 8, I'm going to reduce that strength to 2. Whereas the first magnet, it had a strength of 2. I'm going to move that up to 8. I'm going to hit Setup, and for now, I'm going to leave the initial speed of particle A to 2. We're going to watch what happens. As A is coming in, it's clearly showing that that is not enough speed to break the bond between B and magnet 1. So I'm going to pause this, and I'm now going to increase the speed of A to 4 instead of 2. Hit Setup again and go. Let's see if that is enough to kick B off of object 1, and B is now forming a bond with magnet 2. Clearly, particle C left the system at a much lower speed than the original speed of particle A, because magnet 2 is weaker compared to magnet 1 in this third condition. Let's summarize these three conditions one more time. The first condition, where the two magnets, 1 and 2, had the exact same magnetic strength, particle C left the system at a slightly reduced speed, probably because there are multiple forces at play here, not only the incoming speed of green particle A, but also the magnetic forces of both magnet 1 and magnet 2, thereby reducing slightly the speed by which particle C left the system. For condition 2, the second magnet had a greater magnetic force than the first one, and therefore you can see that particle C left the system at a greater speed than the incoming speed of particle A. Stronger bonds were formed, weaker bonds were broken. For the third condition, the first magnet had a much greater magnetic force compared to the second magnet. And as you can see from our speed diagram, particle A came in at a much higher speed, which was required in order to break that stronger original bond. And particle C left the system at a much lower speed because the second magnet had a much weaker bond. So stronger bonds needed to be broken, weaker bonds were formed. So let's connect lesson 10 all the way back to the very first lesson of the chemical bonding storyline, when we had our students do the experiment that involved a beaker getting all stuck to a wooden board because we had two chemicals in there that combined and completed an endothermic reaction. So stronger bonds were broken and weaker bonds were formed, very similar to the screenshot of the simulation shown here. Alternatively, in the second part of this bonding storyline, we had the students complete the alkali metal in water reaction, clearly an exothermic reaction during which weak metallic bonds are broken and much stronger ionic bonds between the alkali metallic ion and the hydroxide anion were formed. And that matches with the following screenshot, where the strength underneath the second magnet is much stronger compared to the strength underneath the first magnet. This perfectly leads us into the next lesson, lesson 11, with the following central question. How do scientists represent the changes in energy in endothermic reactions that feel cold and exothermic reactions that feel warm to the touch? And of course, the hint here is that this is when we finally have our students connect what they've observed in the lab and in the simulation to the potential energy diagrams shown on this slide. As always, the chemical bonding storyline is associated with Next-Gen Science Standards and New York State Science Learning Standards, including HSPS 1, Matter and its interactions, as well as HSPS 3-1, Energy Change in Components of a System. All the 10 lessons so far, including the 7 lessons that were part of the first part of this bonding storyline, have been chronicled, and they've all been placed in one playlist called the Stunning Storyline playlist. And that concludes lesson 10 of the chemical bonding storyline. If you're interested in these resources, go to the video description below. There's a link. When you click on that link, in exchange for your email, you receive the following Google document with all the handouts and associated teacher keys for you to use in your classroom. Thank you very much for watching. Bedankt voor het kijken. Tot ziens and see you in the next video.